Very much for, well, Hussein and the other organizers of this wonderful event, which I'm actually quite, I'm impressed and enjoying very much. So I just, well, before I give you some history snapshots, I just introduce my topic of my talk. So, well, I'm a collision theorist and I don't speak German. right here, right among ITAMP postdocs, where I was here from 2008 to I think 2011 or 12, and most 90% of what I've been doing is collision theory. So, but recently we've been kind of branching out to quantum information science with ultra-cold molecules. I'm going to talk about some quantum algorithms that we developed for collision problems together with our collaborators at University of Toronto and UNR. So, okay, so these are my people here at ITAMP, so the people that really affected me, most perhaps. And my postdoc advisor, Roman Krems, actually introduced me to ITAMP. And then I met Alex Delgarno and Hussein, and Alex Delgarno is, is the person who perhaps determined my scientific career or the trajectory. And as we always, we know that initial conditions often determine the, later dynamics. And this was the case in my case. I'm still figuring out what Alex, he has a lot of papers, and his students have amazing papers. And in fact, he was more like a mathematician more than in my view, the theory, because he had extremely wide reach and also strong mathematical skills. And this is something that I admire about Alex most, because he believed that what we learn in physics is not in the equations, but in the solutions to these equations. And so solving the differential equation, was one of the strongest skills that I learned from Alex, and developing proper basis sets, and so getting the solutions right, right. So that's kind of the message that I got from Alex. But of course, here I met all the amazing experimentalists that I still collaborate with, and I'm immensely grateful for that. John Doyle, of course, June, Kangquen, and Wolfgang, and I've enjoyed very interesting conversations with Misha, Seth, Bala, Bob, and now we collaborate with Anna Maria. So pretty much, I would say 90% of my collaboration started here. So, and I'm immensely grateful for that. So now I'm going to show you something. So, so this is a three-body problem. Okay, so you see this is just a small fraction of periodic solutions to the three-body problem. If you can find in Wikipedia, it's actually very relaxing. You can just watch it, sometimes watch it when I'm having, stressed at work. So, there's thousands of these have been, and new ones are being discovered. Actually, a few years ago, some Chinese scientists discovered another 1,000 of those solutions. So it just gives you, I just follow up on what Misha said in the previous talk, that complexity grows very quickly, right, as a function of number of particles. So we have two particles, we only have a few of them. Right now we have thousands and not yet discovered all of them. So it's just you have a leap from very limited number of solutions to almost thousands of them, right? And then four-body problem, I'm not even showing this. So my group at UNR, I'm a theoretical molecular physicist. We study all kinds of collision processes, and I'm the opposite of Misha in this respect. I am obsessed with collisions, right? So that's mostly what I do. So, and some of the highlights, these studies include our recent papers with Wolfgang's group on observations of Feshbach resonance in molecule-molecule collisions, and surprisingly long-lived Feshbach resonance, which is still awaiting its theoretical explanation. So no one pretty much knows what's going on and why it's so long-lived, and it was very surprising. This study of quantum ergodicity that we started when I was on sabbatical at GILA last year or 2 years ago, and this amazing work we have been, I've been very excited about generating entanglement with polar molecules and optical lattices. And now I'm going to tell you about today is, let's see if this works, mostly this. Is this how do we use quantum computers, or can we use quantum computers to actually solve interesting multi-channel reaction problems in chemistry, quantum collision problems in chemistry? So these are the kind of problems that Alex would be interested in. So But we also do all kinds of quantum control. So please feel free to ask me about it. I wish I could talk about all of that. But anyway, so molecular physics is interesting, right? And molecular spectroscopy, you kind of already saw this graph. So Misha, thank you very much for selection rules. I don't have to explain them anymore. But the point is that molecular spectroscopy is still going strong. So there's still very active field. And in astrophysics in particular, this is pretty much the only tool we have for identifying molecules that exist out there in the interstellar space and exoplanet atmospheres. And of course, it's not just spectroscopy, it's also chemical reactions. So it's mostly like a chemical dynamics, and all the chemistry is really just the Schrödinger equation, right? So it's either for electrons, but we assume that we already solved the electronic structure problem. So we got the potential energy surface, and then we are interested in solving the nuclear Schrödinger equation, right? So this is a very difficult problem, all right? So that scales exponentially with the number of atoms. Just to illustrate this, I just found this interesting paper recently on some proteins maybe forming in the atmosphere of exoplanets through collisions. And this molecular complexity is starting from carbon atom, carbon monoxide, ammonia, and simple molecules, right, that they exist in the atmosphere on these planets. They actually combine to build up this very quickly, this incredible complexity, right? And that's where we are currently. Our understanding is limited here. So once we start getting into these large molecules, right, our theoretical tools fail because of the exponential scaling of the computational effort, right, with the number of atoms. Just like all of these wonderful talks that I heard earlier today with large many-body systems, we have this complexity, except that in molecules, you can actually grow the complexity just one atom at a time. So you can actually have the luxury. I'm studying ammonia. Ammonia is something that we can still calculate, but this guy is already on the verge of impossible. This is like very, very hard to do. And why? Because it's a large molecule, a lot of modes. And if you try to simulate it in a classical computer, scales exponentially, especially chemical reactions. So you cannot describe chemical reactions of two peptide molecules. We don't know how they form. So, and this is a very important thing because we eventually want to be able to understand how this life emerged, right? Let's say. But of course, chemistry is an active field. People care about molecules and how they interact and react with each other, right? So we would like to be able to simulate, but we hit the wall, right, with exponential scaling. So. Now, my field of really, what I really love about collisions is that we can go to ultra low temperatures by cooling molecules, and there is a lot of mysteries currently in the field. So we know from this, let's say if you look at the review of this Lua and Emmanuel block, that if you put two diatomic molecules, someone mentioned three-body collisions as a major impediment to, well, Richard mentioned, as to quantum simulation with Feshbach resonances, right? Well, for molecules, two-body collisions are actually a major impediment because when they collide, no one knows what's going on. No one, because they just stick, well, they lose. We observe loss, or many experiments observe loss in two-body collisions, right? When the density is very low. So what's going on? Well, people think they just stick, they form these collision complexes, right, like this, and then they dwell in these complexes for a while, and then they separate, right? So can we understand that? Can we simulate that? Just like we did, we were able to do it very well with ultra-cold atoms. Ultra-cold atoms, like if they also form this kind of long complex, not so long-lived as molecules, but sometimes pretty like they get together for 5 or 10 vibrational periods, and then they separate. We can simulate this very well because atoms, they don't have complicated structure. We have just a few states. We can solve the Schrödinger equation, on a laptop, pretty much, for this system. Like this one is tremendous leap, a quantum leap in computational complexity, which, it's not boring because every molecule collides in its own way, right? So, and the lifetime for these complexes vary by many orders of magnitude, depending on the molecule. But the answer is still, the jury is still out. No one really knows what. It's one of the major mysteries, according to many well-respected people in the field of ultra-cold molecules, that can potentially, it's a problem because we don't understand what happens when they come together, right? So in principle, we could solve the Schrödinger equation, but classical calculations take forever on a classical computer. So other mysteries exist as well. So, so how do we proceed, right? Well, Of course, the solution, as we know it, right, currently, perhaps one of the promising ways, most promising ways forward, is to use quantum algorithms, and in particular, quantum phase estimation algorithm that is, of course, fault-tolerant quantum algorithm that I am tempted to say it's currently limited by errors, but after Michel Lukin's talk yesterday, I don't know what to say. So it's probably not so much limited by errors anymore. So we can do we can do better, right? But anyway, so this is the dream, right? That we can do this Kitaev's phase estimation algorithm on, of e to the time propagator, right? And estimate the phase, get the eigenvalues. Seth Lloyd wrote, fundamental papers about this, and eventually this is what we'd like to be able to do. But unfortunately, right now, there are a lot of errors, and so we are limited to NISQ algorithms, and well, these are not the only alternatives, but the two of them that I'm most excited about, the NISQ algorithms and quantum simulation. So NISQ means, well, it's this acronym that was, I think, invented by John Preskill to address this intermediate stage between, fully fault-tolerant quantum computers and the ones that are not fault-tolerant. So we can actually make, perhaps, the idea is to make them work in tandem, the quantum and classical computer together, right? And one of these, iconic techniques or algorithms in this, domain is variational quantum eigensolver, which was, I think, pioneered by Alan Asper-Guzzi group, who is now at the University of Toronto. So the idea is basically you make them work together. So you create, let's say, you want to estimate the energy of hydrogen molecule or water molecule. So you basically calculate the expectation value on a quantum computer, and then as a function of this parameters theta, and then you make this classical computer, you vary in these parameters, and then you actually try to optimize the expectation value such that you reach the minimum of energy, right? And so this has been demonstrated for many molecules successfully. So we know that this VQE, it actually works, right? So can we actually do something similar for scattering, right? But before I get to that, the answer is yes. We heard yesterday from Misha this programmable quantum simulators now available. So if we can map our collision system into a spin model, let's say lattice spin or spin boson model of some kind, then the quantum dynamics of the system can be evolved, can be directly simulated on a quantum computer, and then the correlation functions at long time limit, they can be measured, and all these properties of the systems can be extracted, let's say spectral weights as a function of frequency. So giving us essential information about quantum systems. So and a number of platforms have, we know that it can be done for a number of many body systems. Has been done already on trapped ions. As far as I know, trapped ions are limited, the kind of spin models you can simulate. So that was that, I wasn't very excited about simulating quantum collision dynamics, but when I saw this paper, I thought, okay, this one can simulate products of more than 2 spin operators. And that for me was, a signal that maybe it's time to develop some quantum simulation algorithms for quantum collision physics. And I'll show you how in a second. So, but before I begin with, our NISQ algorithm, which is based on a convariational principle and variational quantum linear solver, which is based on VQE, variational quantum eigensolver. And then I'll tell you how to actually use quantum simulation to simulate, quantum dynamics of chemical reactions on programmable quantum arrays. So, first of all, we need a variational technique, right? So to simulate collisions. And the first thing and the best variational principle for collisions is actually called the S-matrix convariational principle. So it's very similar to the standard variational principle, but you calculate the S-matrix instead of just the energy expectation value, right? Like you do in the normal variational VQE. So the key quantity of interest in chemistry is transition probability, right? So from one state, initial state n sub I, to some final state n sub f, which is just the absolute square of the S-matrix element. So you basically calculate the expectation value, which is just slightly different from the expectation value that you would get in a normal variational principle. The key principle is that this is a complex quantity. So you calculate the transition amplitude, and this is at a stationary point. It's not a minimum, right? And this is one of the limitations of this convariational principle. But it's known to be one of the best techniques. It was developed by Bill Miller in the 80s at Berkeley. So that was really one of the first methods actually that people used to solve quantum dynamics of chemical reactions exactly on a classical computer. In 1989, Bill Miller's group actually applied it to to solve the D plus H2 reaction on a classical computer, and that was a huge step forward. Now, I mean, it started the whole field, but now it's kind of fallen out of favor. So maybe, but when if you use the right trial functions, this method can be incredibly effective. So it can be very, very efficient. So basically, the trial functions in a normal variation method are just like some basis functions, but in the scattering, there's a twist, because like you have to make the wave function such that, or you choose it such that it satisfies the correct boundary conditions. Otherwise, it's not a scattering process, right? So that you make sure that you have translational basis functions that do not vanish at infinity. So they satisfy the correct boundary conditions. And then you have these internal basis functions, just like in the normal VQE. And then you have additional set of basis functions that I'm not going to talk about. It's just like for technical issue. Okay, so I hope everyone is on the same page, on the board with this. So now we plug this one. All we have to do is plug this one here and do some minimization, right? Or extremization of this functional. And we end up with this expression. So basically the S matrix is actually equal to some B matrix plus this product of three matrices pretty much. But this B matrix is actually, it depends on the inverse of certain matrix M. And M is essentially the matrix of the Hamiltonian in the L2 basis, in the basis of the same basis you would use in the class, in the normal VQE, standard VQE. So basically, like all we have to do, instead of calculating the minimum, minimizing the functional, we calculate the inverse of the matrix of the Hamiltonian. But how do we do inverse, right, on a quantum computer? Well, there is an algorithm for that. It's called VQLS, developed by Patrick Coles at Los Alamos. So there are other algorithms. This is not the only one. People are still developing them. I saw one recently developed by some Russian scientists. It seems like very promising. But this one was the first one. So basically, it allows you to solve a linear system of very large size, exponential size in the number of qubits, right? With a given right-hand side, which you basically create a quantum circuit for. So you have to do two quantum circuits, one for the right-hand side and one for the parameterized solution, x of theta, right? So the idea is basically you parameterize this x sub k, and then you use VQE to vary this x sub k variationally, right? So you change the parameters variationally until the solution actually matches the right-hand side, right? So it's very similar to the VQE, except that, you have a given right-hand side to satisfy. So you basically choose this. So let me explain a little bit detail. So basically, you first parameterize the right-hand side using some standard quantum circuits by acting, zero is just a zero state of n qubits, and then you act by a unitary operator to have your, unit matrix in this case. Then you have the solution circuit, which actually looks like this. It's pretty standard quantum circuit for VQE. It's called hardware efficient ansatz, right? So there are two kinds of classes of ansatzen in this. Sorry, I don't speak German, but it's in VQE. We have hardware efficient, and I think another one class is called system stimulator or system inspired or something like that. Anyway, so there is a lot of papers on how to choose the most efficient ansatz, but here we just go with the most basic one, which basically has a bunch of single qubit rotations and C0 gates, right? So it's nothing new. It was developed before a few years ago, so we just took it off the shelf pretty much and expanded the matrix. One crucial element is you have to expand your matrix M, which is essentially the Hamiltonian matrix for the collision, in polystrings. So you expand it in products of spin operators, spin 1/2 poly operators from SU2 essentially. And then once you do that, you minimize your cost function, which is just which has this operator as implemented on the quantum circuit, and you're done pretty much. So that's the basics of VQLS as we described in this paper. So how do we apply this? So let's pick an interesting system to apply. So the system has to be picked up with care, because we don't want a very large Hamiltonian, right? So we want some interesting Hamiltonian, that's modern Hamiltonian, but not super hard, so that our computers quantum NISQ algorithms cannot solve it. So we basically picked up a standard Hamiltonian in chemical physics known as the reaction path Hamiltonian. So the reaction path Hamiltonian describes a lot of processes. It's not necessarily a reaction. It can describe spectroscopy of highly vibration states, isomerization, like right now, isomerizing, like, because you see me today, your retinal molecules in your eye are working pretty much and isomerizing, described by this Hamiltonian. So because of that, you can actually, it's generic. So this is just one example. What is this capital P is the conjugate momentum to the reaction path. What is a reaction path? Is a path of steepest descent from the transition state. Let's say you have a reaction with a barrier, all the way, to the reactants, and all the way down and back to the products. Okay. Mm-hmm. So, and this is just the paper we wrote with Roman. It was solved. I mean, it was a classical computer, but anyway. So the point is that there are two types of coordinates in chemical reactions. One is this reaction coordinate where you have large amplitude motion, right? So you go from reactants to product like this. It's not limited, okay, or scattering, if you will. And then there's like a small coordinate, like vibrational coordinate perpendicular or orthogonal to the reaction coordinate. So you basically are not allowed to go beyond certain limit on that coordinate, right? So you can use vibrational basis functions, which you can then map onto qubits. And that's the idea of this method, right? So, okay, so we basically can qubitize this Hamiltonian, right? And then with just 2 degrees of freedom, we are able to actually get pretty good results compared to, for the vibrational transition probability between the two vibrational states in this model 2-dimensional reaction path Hamiltonian, okay? Some people are smiling. People who understand chemical physics are smiling.
What's the scale there?
It's dimensionless collision energy in units of vibrational frequency of the oscillator. This Hamiltonian depends, it's basically oscillator, harmonic oscillator colliding with an atom, right? And it's a linear collision, so it's a collinear system. It's not a 3-dimensional. 3-dimensional would be a next step, right? Like including rotations is, not for the faint and hard. So we haven't done that, right? But the point is that for very large molecules, actually including rotations is not important, because very large molecules are totally dominated by vibrational degrees of freedom. If you have a large molecule like with 10 atoms, then it has like 3n minus 6. 24 vibrational degrees of freedom and just 3 rotational degrees of freedom. So sorry, Misha, rotations are not important for very large molecules. Okay, we only care about vibrations, and so that's what we do. We include them. And okay, so it works very well for this kind of system. So we're thinking, like we can probably, as a next step, describe more complicated reactions or reaction of retinal, let's say in our eye, also on a model level, all kinds of extensions are possible here. Okay, so but I think I have 4 minutes, 3 minutes, and lunch is important. So I just want to tell you about very recent work, not published yet, and on how can we map this reaction path Hamiltonian onto a spin model. So this was important for simulation of programmable quantum simulators, right? So if we start with the reaction path, we expand out the potential in harmonic modes near 0, right? So now this is a fully general case. So n-dimensional polyatomic molecule. So, and then we introduced the basis, right? So and then here's a twist. You have one basis for a very large reaction coordinate, which changes from minus infinity to plus infinity. And then you have this basis for vibrational modes that are orthogonal to the reaction coordinate. So which we map onto qubits. So we map onto qubits this one separately from this string, right? So that's what we do. So, and that's not hard. We just have to calculate the matrix elements, right? So basically the Hamiltonian is just a bunch of jump operators, right? Times matrix elements is a sum, just like you do in like, introductory level quantum physics. And then the matrix elements are not so obvious because they have 2 classes of matrix. There are 2 classes. One is over these translational functions of the large reaction coordinate, and then the second class of matrix elements over vibrational degrees of freedom. But the nice thing is this is just, if you pick a few vibrational coordinates here, like let's say 2 lowest mode of the harmonic oscillator, you can easily map it. Let's say this matrix element is just like Sx. Right, and this is like Sy or something like this, Sx, and then this is Sz. So it becomes very nicely mappable onto some sort of a spin model, which looks really weird. So I've never seen a spin model this before. So it basically has a Pauli string expansion of translational degree of freedom. It's like this one has a lot of terms, but there's only one translational degree of freedom. So it's not bad. Okay, so you can live with a lot of terms here. I know some people care about, like we had a lot of this large degrees of freedom, then it would scale exponentially, so this wouldn't work. But because we have only one of these large amplitude motion degrees of freedom, it actually, we can live with its scaling. It doesn't affect the scaling. The key difficulty here comes from this, a lot of vibrational degrees of freedom, which come into this, we can qubitize them as vibrational qubits here. So they also mapped onto spins, at least the two lowest, ones, naturally mapped into spin 1/2. So we have a spin model that has, the essential coupling is like Sx with all kinds of Pauli operators for the scattering coordinate, and Sx, Sy, Sx, double Sx with a lot of other operators in the scattering coordinates. So this is very new. I derived it yesterday, I think. So, but it looks doable. So at least for this two-dimensional Hamiltonian. So just want to conclude that it's a very interesting field. How can we solve quantum dynamics from chemical reaction on quantum computer? So we can do either NISQ algorithms based on quantum BLAS, if you know what I mean, like quantum inversion, right? If quantum Laplace BLAS. And then, or we can do the quantum dynamics on a programmable quantum simulator, hopefully by mapping this quantum spin model onto or quantum chemical dynamics onto a spin model. So I'd like to thank you all for your attention.
Very nice. Any questions, comments for Tim?
So you also here mentioned again this exponential wall in the calculations, but if you do molecules and then you're interested probably in the finite set of interesting functionalities molecules would have, and somehow it seems that you could reduce the information content also here going in your calculation. So, and you represent this in approximations you take. How could you implement something like this on your quantum algorithms, or how do we learn? I mean, what do you really learn if you would solve it exactly on the quantum computer? What do you do with all that information?
Well, I'd learn, for example, how two molecules react with each other, right? Like what's the reaction rate, right? For example, the thing with astrophysics, right? They want to know the reaction rates of these polyatomic molecules. Actually, even the collision rate of two water molecules, I think Bala told me recently, is an open question, right? You cannot even calculate on a classical computer if you want accurate results. The astrophysically extremely important case of two water molecules colliding, right? Not all, of course, this is, let alone these more complicated molecules. So if you can know the cross-section can be obtained from the solutions of this Hamiltonian, from the long-time dynamics of this Hamiltonian, which you Fourier transform and basically project onto, like energy basis, and you calculate the cross-section as a function of energy.
Calculating just one correlation, that's just one correlation function you're interested in. And it seems like you have a ginormous overhead by solving the full problem.
Oh, okay, I see. There are methods using actually reaction path Hamiltonian that bypass this summation, also developed by Bill Miller. And they also require time dynamics, time propagation, so all these spin models, mappings could be useful there as well, but there are methods like that, yeah. Yeah.
Hi, Timur. Really great talk. Great talk. Do you see any exponential scaling of this algorithm? Like, where is it actually implemented? In a real quantum computer or a quantum simulator?
Oh, the NISQ one, we just did the Qiskit implementation, right? So, but it could be implemented on any platform in principle, right? We just take VQLS off the shelf and we do it. But the spin model hasn't been done. I just, it's a very new thing that I was motivated by Misha's paper, so essentially, yeah.
Let me follow on those questions. So how does it scale with the number of channels per qubit? Or how many qubits you need per channel?
Depending on your basis. So if you have just two vibrational states, one per vibrational mode. If you have four, you need, 2 to the power of log, and the log of the number of vibrational states you include per each mode.
Yeah. So to be interested, you need a big system. Don't you need
Sure.
a number of qubits?
Yeah.
So actually, I have like 3 questions, but it's lunch coming up, so I don't want to. So maybe I will try to maybe with 2. So the first one is what do you call it? VQLS, whatever.
VQLS.
Yeah. So I'm a bit worried because it means basically this kind of linear system of equation. Solving these algorithms, that they require this thing called QRAM.
Mm-hmm. No, I don't know, but okay.
Actually, no, but I mean, like, I'm not sure if they scale favorably. So, I mean, this, quantum computers are very, efficient in terms of like inverting matrices, multiplying, manipulating, but then you need to account for the cost of loading.
Sure.
Of the information, and that actually usually...
Like you mean preparation of the...
State preparation,
yes.
And kind of read out and instructing, usually it's actually, you hide kind of exponential cost in there, so...
Yes, that's correct.
Okay, so I'm not, I think it's a nice example, but I'm not completely sure how useful it is at the end. But so, for your second question, I think it looks super cool, but I'm sort of wondering if, for example, like this sticking collision, it would be super cool to use quantum computers to analyze them. But so where is the complexity of this problem coming from? So like if for the many-body problem, it's clear you have an exponential dimension. So here, where is the exponential, why is it hard classically, and how do you think this helps to overcome it?
Well, okay, it's a very good question. It means that I don't know the answer to 90% of this question, but I know probably the answer about 10%. Okay, so sticky collision problem is extremely hard because of rotational degrees of freedom, not because of vibrational degrees of freedom, because they rotate, and this strongly anisotropic potential and deep one couples hundreds of rotational states, which are very hard to include. Even 2 water molecules cannot be done, let alone KRB would require way more resources. There are tricks, classical tricks we're actually working in our lab to implement. We think we can solve 2 Regio rotors, we hope. But rotations is the issue, can be mapped. 100 states for each molecule, rotational state, and then hundreds on another, and then in internal angular momentum states. So the basis set you need about, I estimate about 10 million would be required channels.
10 million. So
and
look at 10 million.
Right, but for the scattering algorithms, they're extremely, we're still using scattering algorithms from the 50s. Like last year, we celebrated the most widely used Johnson log derivative algorithm has been 50 years old. So very, old school. So maximum number of channels we can currently solve, actually Roman and I solve 18,000. And we spent like half a year per data point, right? So on a big cluster. So, okay, and we're looking... It's a continuum as well, yeah. So we have to, it's a very special technique.
Yeah, you need to time evolve.
Or propagate. You need to propagate, yes. So it's 20,000 is at most what we can do currently. So, and Philip knows, and I guess you can come, but the rotations could be, we thought about rotations too, but that will probably need some sort of synthetic dimension for that. So like along the work of Cad and Hazard at Rice, right? So they have this, they can encode rotations into synthetic dimensions, but maybe what Misha does could be useful, but I don't really know the answer.
We're going to continue this at lunch.
So let's thank Timur for reading.